Hello, everyone. My name is Han Wang. Today, we will introduce a new programming model for distributed computing, Fugue, to unify Spark and non-Spark ecosystems for data analytics in Python. We are going to explain our motivation, and then we will talk about Fugue core, Fugue SQL, ML, and streaming. After that, we will go through Fugue use cases. In the end, it's our open source plan. Working on different big data problems, I find that I always have to re-evaluate the frameworks I'm using. And in order to be scalable and fast, I always have to figure out special treatments. I think the problem is we have too many options. Each of them is great at certain things, but many of them are overlapping. And many of them try to exclude other options. So what if we can have an abstraction layer to unify different ecosystems? What if we can focus on describing what to do instead of how to do? Plus, this layer should not prevent direct usage of any underlying systems. This is the motivation of Fugue. It is a pure abstraction layer. It is to unify and simplify the core concepts of distributed computing and to decouple your logic from any specific solution. It is easy to learn and easy to onboard and offboard. It's not invasive, not obstructive, and not exclusive. It is not something to hijack your project. For example, Node2Vec is a great idea for graph embedding. The authors of the paper open sourced this algorithm in native Python. But when we try to apply it on large-scale graphs, it couldn't work, so we want to redesign it. The original version is built on NetworkX library on top of native Python. We decided to use operations join and transform to replace NetworkX. So we no longer have single machine constraint. By the way, in Fugue, transform is similar to map partitions and group by key operations in Spark. We use Fugue workflow to coordinate join and transform operations, so it's purely abstract and can run on native Python, Spark, and Dask, whatever Fugue supports. Later in this presentation, Jintao is going to show its great performance. But first, let me show you the Fugue code. Over 90% of the source code is pure native Python. So I didn't put them here. Here, the first 15 lines of Fugue code is everything we need to express the high-level logic. And line 18 to 20 shows how to run it on native Python, Spark, and Dask. You just need to change one parameter. Now let's take a look at the core of Fugue. On top of different computing platforms, we firstly build an abstraction layer called execution engine. It's an abstraction of basic operations such as map, partition, join, and SQL select statement. On top of execution engine, we use directed cyclic graph to describe the workflow. This is similar to Airflow. And then we add the programming interface and built-in extensions such as save, load, and print. On the top level, we provide a new way to express your workflow, Fugue SQL. We also have machine learning and streaming features to be released later this year. So what is special about the Fugue programming model? First of all, it's cross-platform. Fugue workflows can run on different Fugue execution engines. Fugue is not only adaptive to the underlying systems, but more importantly, it's adaptive to users. In order to use frameworks such as Spark and Beam, commonly you have to use their interfaces, decorators, or data frames. You adapt to the frameworks, but in Fugue, the framework adapts to you. With this programming model, you can keep majority of your logic in native Python with no dependency on Fugue. Also, if you migrate something onto Fugue, you can also keep most of your code untouched. Testability is another pain point of distributed system, but Fugue makes it easier. It helps you write modularized code to keep most of your logic native, which is easier to test. For the part involving Fugue, because you can run with native Python execution engine with small mock data. It's also easier and faster to test. For example, we achieved 100% unit test coverage on Node2Vec using native Python execution engine. We also run these tests on local Spark. It's over 10 times slower. Let's look at a workflow example. From line 1 to 12 is native Python. Fugue starts at line 14. +n and +npd are doing the same thing, but with different signatures. We use both of them as transformers at line 16 and 17. And Fugue adapts to your native functions and provide the data types according to the type annotations. Here, +npd is used as a map partitions function, and +n is used as a group by apply function. In Fugue, transformer unifies the two concepts and can use native Python code directly. Now let's have a closer look at Fugue extensions and the DAG. The Fugue DAG consists of 5 different types of nodes, all we call extensions, and the edges of the graph are strictly schemaed data frames. On the driver side or orchestration side, we can customize creator, processor, and outputter. Each arrow means an input or output data frame. On the worker side or computation side, we can customize transformer and co-transformer. Actually, you can write native Spark code inside any driver side extension. This architecture does not stop you from using any native Spark features. There are benefits to use DAG. Here is an example. Given a data frame, we run mapper A and let result be X. And the next 2 steps run different mappers B and C on X and save separately. If you write this in native Spark, the execution order will be A, B, A, C, which is counterintuitive. If you add persist on the first step, then it becomes A, B, C. But using Fugue, with auto persist enabled, B and C will run in parallel after A is auto persisted. So in Fugue, intuitive expressions can generate optimal executions. However, in order to achieve the same thing in Spark, you need extra effort. Besides auto parallelization and auto persist, there are other benefits to use DAG. More errors can be captured when you construct a DAG before you submit a Spark job, so you can fail faster. You are also able to resume an execution with checkpoints. Please notice the difference between persist and checkpoint. Persist is to cache for the following tasks. It will be cleared after one execution. Checkpoint is to cache for multiple executions. It will be kept after one execution. As I mentioned, we created a new approach to describe your end-to-end workflow, the Fugue SQL. Let's look at an example. We create a data frame by create statement and assign to A. Then we transform it using +n and partition by K. Then we use the standard SQL join statement. Then we have a simplified anonymous select statement, and we print and save this data frame. And then we are doing an expensive transformation on B. Notice the double question mark after DF means checkpoint. In the end, we use another outputter extension to assert the 2 data frames are equal. Here is a comparison between Fugue SQL and Spark SQL. The main difference is that Fugue SQL is on workflow level and Spark SQL is on task level. Fugue SQL enriched Spark SQL and can glue Spark SQL and Fugue extensions together to be an end-to-end workflow. Also, Fugue SQL is cross-platform. It can run without Spark. In addition, Fugue SQL supports caching and checkpointing. Although it is SQL-like language, it is designed for workflows. It's worth to mention that if running on Spark, Fugue also supports Spark UEFs. The features of Fugue SQL and the programming interface are in parity. However, they can put you in different mindsets. For example, I want to partition a data frame by a column and get the first record of each partition. If you use programming interface, a transformer seems nice and clean. But if you are in SQL mindset, you may firstly consider using overclose. Which one is better? Different people can have different opinions. But here, we only provide options. Next, my co-speaker Jing Tao will present Fugue Machine Learning and Streaming. Thank you.
Hello, everyone. My name is Jing Tao Zhang. I will be talking about Fugue Machine Learning and Fugue Streaming. Fugue ML has 4 major components. First, we will create adapters to popular ML frameworks so that the Fugue workflow can directly use models created using these frameworks. For example, Fugue can directly train, tune, and infer a compiled model from Tensorflow. Next, we will create an abstract layer for popular ML models. For example, a linear regression model in Fugue can have different backends such as scikit-learn and Spark ML. We will collaborate with the Neural Blocks team on these components. Neural Blocks is a high-level description language for deep learning and has been open sourced by Microsoft. We will also create algorithm libraries for popular ML domains and topics. For example, distributed load-to-wake for graph data, seasonality library for time series data, and more are coming. Finally, we will provide abstract layer of common ML utilities, for example, parameter tuning, data validation, so that users don't have to do duplicate work from time to time. This code block is an ML example of Fugue SQL, and is a demo of how to use adapters and utilities mentioned in the previous slide. Here first, we use a scikit-learn adapter SK model with a training dataset. Next, we specify some common parameter to define the model. The next section is for hyperparameter tuning. The amazing part is that you can conduct model sweeping and hyperparameter tuning simultaneously in a distributed way. In this example, there are three different models to select from: linear regression, linear SVR, and XGBoost regressor. Finally, you can use n-fold cross-validation and scoring for more robust model selection. We have fully distributed the entire process, including model and parameter sweeping, training, and cross-validation. Fugue makes it easy to follow good practice for machine learning. Here is an example ML library, load-to-wake, which has been briefly discussed in the previous slides. The core step of load-to-wake is to randomly walk at every vertex of the graph to generate a large set of random paths as text. These texts are then fed into a word-to-wake training engine for the final embedding results. We have implemented the distributed load-to-wake algorithm on Fugue and use adjacent list to represent our graph, and a distributed breadth-first search algorithm for random walk to achieve high scalability. We use Fugue to do benchmark testing and coordinate load-to-wake computation in various computing frameworks. The blue curve is the runtime performance of load-to-wake code from the original author, and the other curves are for the performance of the same Fugue code running on different execution engine. For the graph with the 1 million vertices, the Fugue version on Spark is significantly faster. This is a great showcase of the flexibility of Fugue and the scalability of load-to-wake. We also conduct testing on very large graph. For a graph with 10 million vertices and 300 million edges, the load-to-wake process takes 2 to 3 hours within 500 cores and 3 terabytes of memory. For the graph with 100 million vertices and 3 billion edges, it takes 6 to 8 hours with 2,000 cores and 12 terabytes of memory. Another ML library is for time series seasonality forecasting. Using common filter, this library has decent performance on even very noisy dataset. It can simulate special events and anomalies in historical data. It can take time series at any intervals, hourly, daily, weekly, yearly. It can handle very large number of time series with seasonality in a distributed way. Fugue streaming is the Fugue components to deal with real-time and near real-time applications. We have a Fugue Spark streaming pipeline in production, which is running efficiently and reliably. We will use Fugue to coordinate abstract layer of streaming connectors to various frameworks such as Spark Streaming, Flink. We have tested Kinesis and Kafka connectors for Spark Streaming, and we are looking for partnership on additional Fugue streaming features. In the next section, I will demonstrate some Fugue use cases. This is the traditional setup of an interactive development environment with Jupyter Notebook. If Spark is used, usually a standby Spark cluster is required. In our case, we use Fugue as an abstract computing layer and entry point to interact with any of the computing frameworks. Our cluster is built on top of Kubernetes, and each user can start and stop their own cluster in their own notebook session. The latency to start a Spark cluster is on seconds level. The system is purely on demand and ephemeral, and we don't use centralized standby clusters. Please be aware that Fugue is an abstract layer and doesn't depend on Kubernetes or Spark. The agility of this system is introduced by Kubernetes and Spark, while Fugue provides consistency, simplicity, and flexibility. In addition, with AWS Elastic File System mounted to each pod, the update of code and dependency will be available in the new Spark cluster immediately, which makes it very agile for data scientists to try new ideas or packages. As Fugue makes code to be modular and consistent, the notebook code can be very easily moved to production phase. We are also interested to collaborate with Li Gao from Databricks to experiment Fugue on very large scale, cross-cluster Kubernetes Spark scheduled by Unicorn. He also has a talk about Spark Kubernetes scheduling in this year's Spark AI Summit. With the system of Kubernetes plus Spark plus Fugue in the previous slide, we have collaborated with quite a few product teams to migrate their legacy pipelines to Fugue pipelines. Here, legacy means training each model in a different computer independently. So if you have 3,000 models, you will need 3,000 computer instances. The migration creates a large cost and runtime saving, increased code testability, and reduced development time. All the migrated projects, the observed performance improvement is very significant. The average total CPU hours has reduced by 74.6%, and the average total runtime has reduced by 83.9%. This is the use case of multi-region regression problem with a few hundred region-based models to be trained and tuned. Each run, the legacy pipeline costs about $630 on all models for more than 7 hours, and the reliability is only about 80%. Fugue pipelines only cost about $23 and finish all models within 30 minutes, and the reliability is 99.5%. In other words, Fugue pipelines have reduced cost by more than 95% and reduced runtime by more than 90%. Another use case is for time series forecasting problem. Suppose you want to forecast the value of some business metric in next week, next month, or next quarter. so that you can have better budget planning and decision making. We have had a few such forecasting models in production. After migrating to Fugue pipelines, the overall cost and runtime saving are both more than 90%. In summary, Fugue unifies various computing frameworks with uniform interfaces. It encourages minimum code change on pipeline migration. Fugue SQL is a larval language of workflows. It can optimize your workflow execution. Kubernetes plus Spark plus Fugue is a great combination with high scale flexibility and efficiency for distributed computing. There have been a lot of real use cases showing Fugue pipelines achieve great performance improvement on cost, runtime, and reliability simultaneously. The Fugue project will build a unified ecosystem for integrating distributed systems and machine learning. We are looking for great partnership from all those who are interested.